Yeah, we're live now.
Okay, great. So, hello everyone. We welcome you to another Kaggle Days Meetup Delhi NCR session, and it is our seventh data catch-up. And we have a really special guest with us this time. It's Mr. Joshua Starmer, founder and CEO of StatQuest. And for those of you who don't know about it yet, StatQuest with Josh Starmer is an emerging YouTube channel in the field of AI and ML, and it's been featured twice by Analytics India magazine. So the topic of today's meetup sketchup session would be understanding neural networks. Now for the agenda of today's event, from 8 p.m. IST to 9 p.m. IST, there will be a session on understanding neural networks by Joshua Stormer. And from 9 p.m. to 9:30 p.m., you can put in your questions, your queries, and they will be taken up by Josh sir. So yeah, over to Joshua sir. Good luck with the session.
Thank you very much. Hello, hello. It's time for StatQuest. Hooray! Bam! So, can we share my screen? There it is. Hooray! Oh, there I am. Hey, can you guys see that? Hopefully you can. So today we're going to talk about neural networks, and we're going to go through three parts because neural networks is a big, complicated thing. So we're going to talk a lot about it. So neural networks, one of the most popular algorithms for machine learning, cover a broad range of concepts and techniques. However, people call them a black box because they are hard to understand what they are doing. The goal of this series is to take a peek into the black box by breaking down each concept and technique into its components and walking through how they fit together step by step. In this part, we will learn about what neural networks do and how they do it. In part two, which we're going to cover today, we're going to talk about how neural networks are fit to data using something called back propagation, which is a whole lot of chain rule. So you'll see a lot of chain rule coming up. And then we're going to talk about variations on the simple neural network presented in this part. And we're going to very briefly touch on deep learning. Specifically, we're going to talk about the Rel U Activation Function. And you'll learn what activation functions are in just a little bit. So if that doesn't make any sense to you, don't worry. Okay, I've got some crazy awesome news. I have a new way to think about neural networks that will help beginners and seasoned deep insight into what neural networks do. For example, most tutorials use cool looking but hard to understand graphs. And they use fancy mathematical notation to represent the neural networks. In contrast, I'm going to label every little thing on the neural network to make sure it's easy to keep track of the details. And the math will be as simple as possible while still being true to the algorithm. These differences will help you develop a deep understanding of what neural networks actually do. So, with that said, let's imagine we tested a drug that was designed to treat an illness. And we gave the drug to three different groups of people with three different dosages: low dosage, medium dosage, and high dosage. The low dosages were not effective, so we set them to 0 on this graph. In contrast, the medium dosages were effective, so we set them to 1. And the high dosages were not effective, so we set those to 0. Now that we have this data, we would like to use it to predict whether or not a future dosage will be effective. However, we can't just fit a straight line to the data to make predictions. Because no matter how we rotate the straight line, it can only accurately predict two of the three dosages. The good news is that a neural network can fit a squiggle to the data. The green squiggle is close to 0 for low dosages, close to 1 for medium dosages, and close to 0 for high dosages. And even if we have a really complicated data set like this, a neural network can fit a squiggle to it. In this StatQuest, we're going to use this super simple data set and show how this neural network creates this green squiggle. But first, let's just talk about what a neural network is. A neural network consists of nodes. So in this example, we're going to call these boxes nodes, and connections between the nodes. So we've got these arrows with numbers on them, and these are the connections between the nodes. Note, the numbers along each connection represent parameter values that were estimated when this neural network was fit to the data. For now, just know that these parameter estimates are analogous to the slope and intercept values that we solve for when we fit a straight line to data. Likewise, a neural network starts out with unknown parameter values that are estimated when we fit a neural network to a data set using a method called backpropagation. And we'll talk about how backpropagation estimates these properties or these parameters in part 2 in this series. But for now, just assume that we've already fit this neural network to this specific data set. And that means we have already estimated these parameters. Also, you may have noticed that some of the nodes have curved lines inside of them. These bent or curved lines are the building blocks for fitting a squiggle to data. The goal of this StatQuest is to show how these identical curves can be reshaped by the parameter values and then added together to get a green squiggle that fits the data. Note, there are many common bent or curved lines we can choose for a neural network. This specific curved line is called Soft Plus, which sounds like a brand of toilet paper. Alternatively, we could use this bent line called Rel U, which is short for rectified linear unit and sounds like a rope. Or we could use a sigmoid shape or any other bent or curved line. Oh no, we've got a terminology alert. Curved or bent lines are called activation functions. When you build a neural network, you have to decide which activation function or functions you want to use. When most people teach neural networks, they use the sigmoid activation function. However, in practice, it is much more common to use the Rel U activation function or the soft plus activation function. So we'll use the soft plus activation function in this StatQuest. Anyway, we'll talk more about how to choose activation functions later on in this series. Note, this specific neural network is about as simple as they get. It only has one input node where we plug in the dosage, only one output node to tell us the predicted effectiveness, and only two nodes between the input and output nodes. However, in practice, neural networks are usually much fancier and have more than one input node, more than one output node, different layers of nodes between the input and output nodes, and a spider web of connections between each layer of nodes. Oh no, it's another terminology alert. The layers of nodes between the input and output nodes are called hidden layers. When you build a neural network, one of the first things you do is decide how many hidden layers you want and how many nodes go into each hidden layer. Although there are rules of thumb for making decisions about the hidden layers, you essentially make a guess and see how well the neural network performs, adding more layers and nodes if needed. Now, even though this neural network looks fancy, it is still made from the same parts used in this simple neural network, which only has one hidden layer with two nodes. So let's learn how this neural network creates new shapes from the curved or bent lines in the hidden layer, boop, boop, and then adds them together to get a green squiggle that fits the data. Note, to keep the math simple, let's assume that dosages go from 0 for low to 1 for high. The first thing we are going to do is plug in the lowest dosage, 0, into the neural network. Now, to get from the input node to the top node in the hidden layer, this connection multiplies the dosage by negative 34.4 and then adds 2.14. And the result is an x-axis coordinate for the activation function. For example, the lowest dosage, 0, is multiplied by negative 34.4, gives us 0, and then we add 2.14 to get 2.14 as the x-axis coordinate for the activation function. To get the corresponding y-axis value, we plug 2.14 into the activation function, which in this case is the soft plus activation function. Note, if we had chosen the sigmoid curve for the activation function, then we would plug 2.14 into the equation for the sigmoid curve. And if we had chosen the Rel U bent line for the activation function, then we would plug 2.14 into the Rel U equation. But since we are using soft plus for the activation function, we plug 2.14 into the soft plus equation. And the log of 1 plus e raised to the 2.14 power is 2.25. Note, in statistics, machine learning, and most programming languages, the log function implies the natural log or the log base e. Anyway, the y-axis coordinate for the activation function is 2.25. So let's extend this y-axis up a little bit and put a blue dot at 2.25 for when dosage equals 0. Now if we increase the dosage a little bit and plug in 0.1 into the input, boop, the x-axis coordinate for the activation function is negative 1.3. And the corresponding y-axis value is 0.24. Let's put a blue dot at 0.24 for when dosage equals 0.1. And if we continue to increase the dosage values all the way to 1, the maximum dosage, we get this blue curve. Note, before we move on, I want to point out that the full range of dosage values from 0 to 1 corresponds to this relatively narrow range of values from the activation function. Excuse me. In other words, when we plug dosage values from 0 to 1 into the neural network and then multiply them by negative 34.4 and add 2.14, then we only get x-axis coordinates that are within the red box. And thus, only the corresponding y-axis values in the red box are used to make this new blue curve. Bam! Now we scale the y-axis values for the blue curve by negative 1.3. For example, when dosage equals 0, the current y-axis coordinate for the blue curve is 2.25. So we multiply 2.25 by negative 1.3 and get negative 2.93. And negative 2.93 corresponds to this position on the y-axis. Likewise, we multiply all of the other y-axis coordinates on the blue curve by negative 1.30. And we end up with a new blue curve. Bam! Now let's focus on the connection from the input node to the bottom node in the hidden layer. However, this time we multiply the dosage by negative 2.52 instead of negative 34.4, and we add 1.29 instead of 2.14 to get the x-axis coordinate for the activation function. Remember, these values come from fitting the neural network to the data with backpropagation, and we'll talk more about that in part 2 in this series. Now, if we plug the lowest dosage, 0, into the neural network, then the x-axis coordinate for the activation function is 1.29. Now we plug 1.29 into the activation function to get the corresponding y-axis value and get 1.53. And that corresponds to this yellow dot. Now we just plug in dosage values from 0 to 1 to get the corresponding y-axis values, and we get this orange curve. Note, just like before, I want to point out that the full range of dosage values from 0 to 1 corresponds to this narrow range of values from the activation function. In other words, when we plug dosage values from 0 to 1 into the neural network, we only get x-axis coordinates that are within the red box. And thus, only the corresponding y-axis values in the red box are used to make this new orange curve. So we see that fitting a neural network to data gives us different parameter estimates on the connections. And that results in each node in the hidden layer using different portions of the activation functions to create these new and exciting shapes. Um, by the way, I don't emphasize this enough. This is the most about neural networks. It's that the connections between the nodes slice and dice the activation functions, and they twist them and they flip them and they rotate them and they use different portions of them. And as a result, they get different curves. So we've got two very different curves. Um, and so now, just like before, we scale the y-axis coordinate on the orange curve. Only this time we scale by a positive number, 2.28. So we're going to do that. Beep, 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 beep. And that gives us this new orange curve. Now the neural network tells us to add the y-axis coordinates from the blue curve to the orange curve. Boop, 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 boop. And that gives us this green squiggle. Then, finally, we subtract 0.58 from the y-axis values on the green squiggle. We have a green squiggle that fits the data. Bam! Now, if someone comes along and says that they are using dosage equals zero point 0.5, we can look at the corresponding y-axis coordinate on the green squiggle and see that the dosage will be effective. Or we can solve for the y-axis coordinate by plugging dosage equals zero point 0.5 into the neural network and do the math. Beep, boop, beep, 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 boop. So we get a very small number as the x-axis coordinate. Actually, excuse me, as the y-axis coordinate. It's a super small number. Now we do this math. Beep, boop, beep, 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 boop, beep, boop. So we get 0.71. Now we just keep going. Beep, boop, beep, 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 boop. We see that the y-axis coordinate on the y-axis on the green squiggle is 1.03. And since 1.03 is closer to 1 than 0, we will conclude that a dosage equals zero point 0.5 is effective. Bam! Now, if you've made it this far, you may be wondering why this is called a neural network instead of a big fancy squiggle fitting machine. The reason is that way back in the 1940s and 50s, when neural networks were invented, they thought the nodes were vaguely like neurons, and the connections between the nodes were sort of like synapses. However, I think they should be called big, fancy squiggle fitting machines because that's what they do. Note, whether or not you call it a squiggle fitting machine, the parameters that we multiply are called weights, and the parameters that we add are called biases. Note, this neural network starts with two identical activation functions, but the weights and biases on the connections slice them, flip them, and stretch them into new shapes. Beep, beep. Which are then added together to get a squiggle that is entirely new. And the squiggle is then shifted to fit the data. Now, if we can create this green squiggle with just two nodes in a single hidden layer, just imagine what types of green squiggles we could fit with more hidden layers and more nodes in each hidden layer. In theory, neural networks can fit a green squiggle to just about any data set, no matter how complicated. And I think that's pretty cool. Triple bam. All right. So we've made it through part 1. And now let's talk about, hold on. Give me a second. Give me a second. Now let's talk about neural networks part 2. Back propagation, main ideas. Bam. Okay, so we just talked about the StatQuest Neural Networks Part 1 inside the black box, and we started with a super simple data set that showed whether or not different drug dosages were effective against a virus. The low and high dosages were not effective, but the medium dosage was effective. Then we talked about how a neural network like this one fits a green squiggle to this data set. Remember, the neural network starts with two identical activation functions, but using different weights and biases on the connections, it flips and stretches the activation functions into new shapes, which are then added together to get a squiggle that is shifted to fit the data. However, we did not talk about how to estimate the weights and biases. So let's talk about how backpropagation optimizes the weights and biases in this and other neural networks. Beep, boop, boop. Note: backpropagation is relatively simple, but there are tons of details, so I split it up into bite sized pieces. In this part, we're going to talk about the main ideas of backpropagation. The first main idea is using the chain rule to calculate derivatives. Beep, 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 beep. The second main idea is plugging the derivatives into gradient descent to optimize parameters. Beep, beep, beep. In the next part, um, which is actually available online, I talk about how to multiply parameters simultaneously, and then I introduce some fancy notation. And then in the final part, I go completely bonkers with the chain rule and show how to optimize all 7 parameters simultaneously in this neural network. Beep, beep, boop. Bam. So we can be clear about which specific weights we're talking about. We're going to give each one a name. This is W sub 1, this is W sub 2, this is W sub 3, and this is W sub 4. And let's name each bias. This is B sub 1, that's B sub 2, and this is B sub 3. Note, conceptually, backpropagation starts with the last parameter and works its way backwards to estimate all of the other parameters. However, we can discuss all of the main ideas behind backpropagation by just estimating the last bias, B sub 3. And in the next StatQuest, which you can see online, I show how these main ideas can be applied to estimate all of the other parameters simultaneously. So, in order to start from the back, let's assume that we already have optimal values for all of the parameters except for the last bias term, B sub 3. Note, throughout this and the next StatQuest, I'm going to make parameter values that have already been optimized green, and unoptimized parameters will be red. Also note, to keep the math simple, we're going to assume dosages go from 0 to 1, just like before, so no big deal. Now, if we run dosages from 0 to 1 through the connection to the top node in the hidden layer, then we get x-axis coordinates for the activation function, just like before, that are all inside this red box. And when we plug the x-axis coordinates into the activation function, which in this example is the soft plus activation function, we get the corresponding y-axis coordinates. Note, we're using different parameters, different weights and biases than we did just a few minutes ago. And so we end up with a slightly different shape for this blue curve. Then we multiply the y-axis coordinates on the blue curve by negative 1.22. Boop, 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 boop. And we get the final blue curve. Bam. Now we run dosages from 0 to 1 through the connection to the bottom node in the hidden layer. And then we get the x-axis coordinates inside this red box. Now we plug the activation function to get the corresponding y-axis coordinates. This orange curve. Now we multiply the y-axis coordinates on the orange curve by negative 2.3. We end up with this final orange curve. Bam! Now we add the blue and orange curves together. Beep, beep, beep. Get this green squiggle. Now we are ready to add the final bias B sub 3 to the green squiggle. Because we don't yet know the optimal value for B sub 3, we have to give it an initial value. And because bias terms are frequently initialized to 0, we will set B sub 3 equal to 0. Now, Adding 0 to all of the y-axis coordinates on the green squiggle leaves it right where it is. However, that means the green squiggle is pretty far from the data that we observed. We can quantify how good the green squiggle fits the data by calculating the sum of the squared residuals. A residual is the difference between the observed and predicted values. For example, this residual is the observed value 0 minus the predicted value from the green squiggle -2.6. This residual is the observed value 1 minus the predicted value from the green squiggle -1.61. Lastly, this residual is the observed value 0 minus the predicted value from the green squiggle -2.61. Now we square each residual, beep, and add them all together, boop, and to get 20.4 for the sum of the squared residuals. So when b sub 3 equals 0, the sum of the squared residuals equals 20.4. And that corresponds to this location on this graph that has the sum of the squared residuals on the y-axis and the bias b sub 3 on the x-axis. Now, if we increase b sub 3 to 1, then we would add 1 to the y-axis coordinates on the green squiggle and shift the green squiggle up 1. And we end up with shorter residuals. When we do the math, the sum of the squared residuals equals, excuse me, 7.8. Hold on, I've got a cough. Something's stuck in the back of my throat. All right, and that corresponds to this point on our graph. If we increase b sub 3 to 2, then the sum of the squared residuals equals 1.11. And if we increase b sub 3 to 3, then the sum of the squared residuals equals 0.46. And if we had time to plug in tons of values for b sub 3, we would get this pink curve. And we could find the lowest point, which corresponds to the value for b sub 3 that results in the lowest sum of the squared residuals here. However, instead of plugging in tons of values to find the lowest point in the pink curve, we use gradient descent to find it relatively quickly. And that means we need to find the derivative of the sum of the squared residuals with respect to b sub 3. Now remember, the sum of the squared residuals equals the first residual squared plus all of the other squared residuals. Now, because this equation takes up a lot of space, we can make it smaller by using summation notation. The Greek symbol sigma tells us to sum things together. And I is an index for the observed and predicted values that starts at 1. And the index goes from 1 to the number of values n, which in this case is set to 3. So when I equals 1, when I equals 2, we're talking about the second residual. And when I equals 3, we're talking about the third residual. Now let's talk a little bit more about the predicted values. Each predicted value comes from the green squiggle. And the green squiggle comes from the last part of the neural network. In other words, the green squiggle is the sum of the blue and orange curves plus b sub 3. Now remember, we want to use gradient descent to optimize b sub 3. And that means we need to take the derivative of the sum of the squared residuals with respect to b sub 3. And because the sum of the squared residuals are linked to b sub 3 by the predicted values, we can use something called the chain rule to solve for the derivative of the sum of the squared residuals with respect to b sub 3. The chain rule says that the derivative of the sum of the squared residuals with respect to b sub 3 is the derivative of the sum of the squared residuals with respect to the predicted values times the derivative of the predicted values with respect to b sub 3. Now, before we calculate the derivative of the sum of the squared residuals with respect to the predicted values, let's clean up our workspace and move these equations out of the way. Now we can solve for the derivative of the sum of the squared residuals with respect to the predicted values by first substituting in the equation. I don't know if you can see in the camera, but my cat is in the room wreaking havoc on the furniture. Um, just a mild distraction. Okay, so now we're going to solve for the derivative of the sum of the squared residuals with respect to the predicted values by first substituting in the equation. And then we're going to use the chain rule to move the square to the front. And then we multiply that by the derivative of the stuff inside the parentheses with respect to the predicted values negative. And that gives us -1. By the way, if this is confusing, if this application of the chain rule is confusing, um, don't sweat it, because I've got a whole video, a whole StatQuest on nothing but the chain rule. So all of these things can be made very clear. So if they're not clear now, don't worry. Just check out that video. Now we simplify by multiplying 2 by -1, and we have the derivative of the sum of the squared residuals with respect to the predicted values. So let's move that up here. Now we are done with the first part. Now let's solve for the second part, the derivative of the predicted values with respect to b sub 3. We start by plugging in the equation for the predicted values. Remember, the blue and orange curves were created before we got to b sub 3. So the derivative of the blue curve with respect to b sub 3 is 0, because the blue curve is independent of b sub 3. And the derivative of the orange curve with respect to b sub 3 is also 0. Lastly, the derivative of b sub 3 with respect to b sub 3 is 1. Now we just add everything up, and the derivative of the predicted values with respect to b sub 3 is 1. So we multiply the derivative of the sum of the squared residuals with respect to the predicted values by 1. Note, this times 1 part in the equation doesn't do anything. But I'm leaving it in to remind us that the derivative of the sum of the squared residuals with respect to b sub 3 consists of two parts. The derivative of the sum of the squared residuals with respect to the predicted values and the derivative of the predicted values with respect to b sub 3. Bam! At long last, we have the derivative of the sum of the squared residuals with respect to b sub 3. And that means we can plug this derivative into gradient descent to find the optimal value for b sub 3. So let's move this equation up and show how we can use this equation with gradient descent. Note, if you're not familiar with gradient descent, check out the quest. The link is hopefully going to be in the description below. I'm not in charge of this. Otherwise, you can find it on statquest.org, my website, or my channel. Anyways, first we expand the summation. Beep, boop, boop. Then we plug in the observed values. Beep, boop, 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 boop. And the values predicted by the green squiggle. Beep. Remember, we get the predicted values on the green squiggle by running the dosages through the neural network. Beep, boop, beep, beep, boop, beep, beep, boop, beep. And now we just do the math and we get negative 15.7. And that corresponds to the slope for when b sub 3 equals 0. Now we plug the slope into the gradient descent equation for step size. And in this example, we'll set the learning rate to 0.1. That means the step size is negative 1.57. Now we use the step size to calculate the new value for b sub 3 by plugging in the current value for b sub 3, 0, and the step size, negative 1.57. And the new value for b sub 3 is 1.57. Beep. Changing b sub 3 to 1.57 shifts the green squiggle up, and that shrinks the residuals. Now, plugging in the new predicted values and doing the math gives us negative 6.26. Corresponds to the slope when b sub 3 equals 1.57. Then we calculate the step size, beep, 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 and the new value for b sub 3, beep, boop, beep, boop, beep, is 2.19. Changing b sub 3 to 2.19 shifts the green squiggle up even further. And that shrinks the residuals even more. Now we just keep taking steps until the step size is close to 0. And because the step size is close to 0 when b sub 3 equals 2.61, we decide that 2.61 is the optimal value for b sub 3. Double bam! So the main ideas for backpropagation are that when a parameter is unknown, like b sub 3, we use the chain rule to calculate the derivative of the sum of the squared residuals with respect to the unknown parameter, which in this case is b sub 3. Then we initialize the unknown parameter with a number, and in this case we set b sub 3 to 0. And we used gradient descent to optimize the unknown parameter. Triple bam! All right, so we've made it through backpropagation. Now, let's talk about the Rel U Activation Function. Give me just a second, and I'll get that ready to go. Beep, beep, beep. There we go. Hooray! So just to review so far, in Neural Networks Part 1 inside a black box, we started with a simple data set that showed whether or not different drug dosages were effective against a virus. The low and high dosages were not effective, but the medium dosage was effective. Okay, so this is all review. Then we talked about how a neural network like this one that uses the in the hidden layer beep, can fit a green squiggle to the data set. Bam. Now let's see what happens if we swap out the soft plus activation function in the hidden layer beep, with one of the most popular activation functions for deep learning and convolutional neural networks. the Rel U Activation Function, which is short for rectified linear unit and sounds like a robot. And as a bonus, because it is common to put an activation function before the final output, we'll do that too. Bam. So we're talking about the Rel U activation function because when you dive into deep learning, people pretty much just use the Rel U activation function all the time. So what we're going to do is we're going to use our very simple neural network to look and see how what that changes and what that means to use the Rel U activation function. Remember, to keep the math simple, we're going to assume that dosages go from 0 to 1. So if we plug in the lowest dosage, 0, the connection from the input to the top node in the hidden layer multiplies the dosage by 1.7 and then adds negative 0.85. Note, these are different parameter values than we've had before, and that's because we're now using the Rel U activation function. So I've decided I wanted to have a neural network using the Rel U activation function, and I fit that neural network to the data, and that gave us new parameter values. And the result is an x-axis coordinate for the activation function. So if we plug in 0 for dosage, then the x-axis coordinate for the activation function is negative 0.85. Now we plug negative 0.85 into the Rel U activation function. The Rel U activation function outputs whichever value is larger, 0 or the input value, which in this case is negative 0.85. Because 0 is greater than negative 0.85, the output from the Rel U activation function is 0. And the corresponding y-axis value is 0. So let's put a blue dot at 0 for when dosage equals 0. Now, if we increase dosage to 0.2, the x-axis coordinate for the activation function is negative 0.51. And again, because 0 is greater than negative 0.51, the output from the Rel U activation function is 0. And the corresponding y-axis value is 0. So let's put a blue dot at 0 for when dosage equals 0.2. And if we increase the dosage value to 0.4, we get 0 for the y-axis coordinate. Again. However, when dosage equals 0.6, the x-axis coordinate is 0.17. Now, when we plug 0.17 into the Rel U activation function, the output is 0.17 because 0.17 is greater than 0. And the corresponding y-axis value is 0.17. And if we can continue to increase the dosage values all the way to 1, we get this bent blue line. Then we multiply the y-axis coordinates on the bent blue line by negative 40.8. Boop, 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 boop. And the new bent blue line goes off the screen. Wah, wah. Note, for those of you drawing this at home, your final bent blue line will have a steeper slope than mine because for the sake of clarity, I'm not drawing things perfectly to scale. Tiny bam. Now, when we excuse me. Now, when we run dosages through the connection to the bottom node in the hidden layer, we get the corresponding y-axis coordinates that go off the screen for this straight orange line. Now we multiply the y-axis 0.7. Beep, beep, beep. We end up with this final straight orange line. Now we add the bent blue line and the straight orange line together. Beep, boop, beep, boop. get this green wedge. Now we add the final bias term, -16, to the y-axis coordinates on the green squiggle. Lastly, because we included the Rel U Activation function right in front of the output, we use the green wedge as its input. For example, the y-axis coordinate for this point on the green wedge is -16, which corresponds to this x-axis coordinate for the Rel U Activation function. And when we plug that into the Rel U Activation function, we get 0, because 0 is greater than -16. And that corresponds to this green dot. Likewise, the y-axis coordinate for this point on the green wedge is -9.2. And just like before, when we plug that into the Rel U activation function, we get 0. And 0 corresponds to this green dot. Now, in contrast to the last 2 points we fed into the Rel U activation function, this one is positive, 0.49. And when we plug it into the Rel U activation function, we get 0.49. And 0.49 corresponds to this green dot. Likewise, the remaining positive y-axis coordinates stay the same, and the negative values are set to 0. And at long last, we end up with this green pointy thing. Double bam. Thus, the Rel U activation function may seem weird because it's not curvy. And the equation is really simple. But just like for any other activation function, the weights and biases on the connections slice them, flip them, and stretch them into new shapes. Which are added together to get an entirely new shape that fits the data. Triple bam! Okay, we've got a technical detail alert. Some of you may have noticed that the Rel U activation function is bent and not curved. This means that the derivative is not defined where the function is bent. And that's a problem because gradient descent, which we use to estimate the weights and biases, requires a derivative for all points. However, it's not a big problem because we can get around this by simply defining the derivative at the bent part to be either 0 or 1. It doesn't really matter. Small bam. Anyways, so that's it. Bam. We hit it. That's the end of my little thing. I guess we ended on a small bam, which is somewhat of an anticlimax. But I hope you guys all enjoyed that and learned a few things about neural networks. I'm super excited because I've just started working on my video for convolutional neural networks and sort of image recognition and facial recognition. It's very similar to these in that I have a very, very simple example that I go through step by step and show you how the math all works out so that we can identify and label 2 different images. So I'm super excited about that. I'm going to be working on that in the next couple of weeks, and hopefully that'll be out in December. All right.
Yeah, great. Amazing session, sir. Rather
Thanks.
bamazing. So, we don't have a lot of technical questions. Maybe you've
Great.
explained the topic so well. People don't have any questions. However, we do have one question there. Let me just. Yeah, so somebody wants to know what tool you're using to present the slides.
I use a program called Keynote. Here, I'll show you. I'll show you what it looks like. It's just like PowerPoint. It's just called Keynote. PowerPoint, you can say, hello. I'm going to say here, we're going to say, Um, hello, hello, India. Bam. And so you can do that, and it's got these little shapes you can draw, and oop, that's more text. And so this is the tool I use. I draw all of my pictures by hand. So, like for example, I drew this because oftentimes when I get like something, and just by the way, just like PowerPoint, you got all these slides over here, and it's just like PowerPoint, but it's called Keynote. I used to use PowerPoint. PowerPoint was fine for a long time, but with my computer setup, for some reason, it crashed all of the time, especially when I was giving presentations. And that's like the worst time to crash ever. And so I was like, forget this. I cannot do this anymore. So I switched to Keynote. The There was a little bit of growing pains, but now I'm going to be honest. I love Keynote. I love it a lot more than I don't mean to endorse it, but it's just for me. It's just it ends up. It's like I do it every day. This is what I do for a living, by the way. I make these presentations, and it's just a wonderful tool to use. Um, so that is the tool that I use. It comes free, by the way. You don't have to buy it. It's a free program. However, you have to have an Apple computer. It only runs on Macintosh computers, or you can run it on iPad or whatever, iPhone even. Um, it comes free with Apple products, I guess is a better way to put it.
Yeah, great. So there's another question.
Hmm.
Yogesh is asking, does neural network always give better prediction than machine learning algorithms?
No, not always. I mean, it's a method. It's just one of many methods we can use. Um, it's not always the best method, and in some ways, it's a worse method than others. Um, Obviously, my example was very simple and very straightforward. Um, uh, we weren't trying to do anything complicated. We had one input dosage values. Oh, there's my cat. We had one input value, dosages, and one output value, whether or not the dosage was effective or not. Um, However, usually you've got more inputs. Usually you measure people's age, their weight, their gender. You might measure a lot of things. Um, and you may have more than one output value. And you're going to have a much more complicated hidden layer situation. And as a result, you cannot draw the pictures of what's going on very clearly. And it's a lot harder to know what's happening. And then it does. The neural networks do become a black box, and that's not always a good thing, especially when you need to know how it's going to behave for unknown input values. And that's sort of like a weird thing about neural networks, um, because you can't always draw the output function in a way that's visible to humans. Um, it's an unknown what it's going to do for all of those sort of new parameter value, no, new input values. I mean, if we input the exact same stuff that we trained on, sure, we'll get something reasonable that we can test and find out. But if we input a value in between the values that we trained on, then it's somewhat unpredictable as to what we'll get. Hold on, I have to let my cat out of the room. uh, I think she might be able to do it on her own. Oh, she's real close. Oh, she's got it. I think she. Oh, almost. Anyways, where was I? Yeah. So neural networks are not always the best thing because they're kind of a black box for unknown or new measurements. Alternatively, you can have things like uh, what are those called? XGBoost, an XGBoost model, which uses trees, and tree based models are sweet because it's real obvious to see what's going to happen for new data, and that's a benefit. So even if the predictions are really solid, sometimes you might want to have a method that's just easier to understand what it's doing. So long answer, unnecessarily long answer to that question. Sorry about that.
All right. So we have another question. How to decide whether to use neural network approach or ML approach for a use case?
Yeah, so like I was just saying, it sort of depends on what you want. If a black box method is okay, and it doesn't really matter if you understand what it's doing and you're not super worried about what it's going to do for unknown input values, neural networks great. Sure, you can, uh, so. But if those things do matter to you, then yeah, you don't want to use neural networks. I mean, all things being equal, if it doesn't matter whatever you want it, you're like, should I use neural network? Should I use a random forest? Should I use extreme gradient boost? Should I use linear regression or logistic regression? What should I do? You can always just use cross validation to compare the methods and choose the one that suits your goal. In terms of accuracy or false positives or false negatives. Just compare them. Um, uh, yeah.
Yes, makes sense. So, another question: how to select which activation function to use and where?
Yeah. So that's a good question. So when you're doing deep learning, um, you just use the Rel U Activation function. You don't decide um, anything that requires. So let me explain what deep learning is. Deep learning is any neural network that has, or this is the definition that I was told, and you may have a different definition out there, but this is just one definition out there. Uh, uh, Deep learning is just when you have three or more hidden layers. So that's not that many. Neural networks computationally get kind of out of control pretty quickly because every node is fully connected to all the other nodes, and each connection has a different weight, um, and we have to estimate all those weights. And so it doesn't take many hidden nodes for things to get out of control in terms of how many things we have to estimate. And it's just been found in practice that the Rel U activation function just works well in those situations. The sigmoid curve, which you see frequently when people use to teach neural networks, is never used for deep learning ever. So that's just not an option. Soft plus maybe, but I think most people just use the Rel U activation function. So I mean, unless you're using doing a super toy example like what I was demonstrating here, you're probably going to want to use the Rel U activation function. One interesting thing you may have noticed in the StatQuest is that when we use the Rel U activation function, we get a very jagged output. And when we use the soft plus activation function, we got a much smoother curve. So it sort of depends on how you want things to be imputed for values in between training data. If you want it to be relatively smooth, or it's okay for it to be jagged. Um, so those may be some considerations. However, like I said, for deep learning, the Rel U is pretty much the default.
So that answers it. Whoa, so we have a lot of questions now.
Okay.
What approach or roadmap would you recommend for someone starting with AI ML from scratch?
um, well, it's funny you should ask that. So if you go to my website, statquest.org, here I'll show you. I'm in the mood for sharing screens. Let's do that. Let's just go and do that. Hold on, give me a second. Let's go to statquest.org. And let me share this so you can see what I see. So you go to statquest.org, and there's this link over here on the right hand corner called a video index. You go click on that bad boy. And the video index has playlists. So if you want to learn statistics fundamentals, you can follow that. If you want to learn linear regression and linear models, you got these playlists we can play with. If you want to learn machine learning, we got a playlist there. However, below that, we have an index of every single video I have made, and it's organized. We have a bunch of statistics fundamentals videos, and these are organized from simple to super fancy. So as you go down, they get fancier and fancier, and they kind of build on each other. Um, And then similarly, I've got all of my machine learning videos organized from simple to fancy and complicated. And we end up all the way down here with neural networks. But we've gone through all this cool stuff. So if you want to learn machine learning and data science and artificial intelligence, you can just pick one of these sections and start from the top and work your way down. It's not that big a deal. I would highly recommend, even if you're not interested in statistics, and you just want to get into machine learning and artificial intelligence, I would highly recommend going through these videos anyways, partly because some of these methods, like linear models, like linear regression, that's a legitimate machine learning algorithm. Um, and these videos explain exactly how it works and how it can be applied in a really wide variety of situations. So I would highly recommend just going through all of them. Start from the top, just work your way down, and you can learn these things. It's personally, I think it's a great way to learn. There are other ways out there. There's a lot of other fantastic YouTube channels out there teaching this material. Mine is just one of many. Um, obviously, you can check out other ones. I'll be honest though, and this is going to sound weird. I actually don't watch anybody else's YouTube channel, so I can't really recommend those off the top of my head. The reason why I do not watch them is my goal is to not copy them. I'm afraid that if I watch somebody else's video on a subject and I'll go, "Oh, wow, they did a really good job explaining that," then I won't know how to do it myself because I don't want to just copy that. I mean, they've already got a great video. I don't want to copy them. Um, and so I just don't watch other people's YouTube videos. I read about everything from scratch. A great resource for that, and this is a free book that you can download, is the Introduction to Statistical Learning in R. It's basically the Bible of machine learning. It's just a book. A lot of my videos follow that book, so it complements it. They complement each other very well. Like I said, it's a free download. It's written by some of the pioneers and the biggest names in the field. Um, and Rob Tibshirani, I don't know if I'm pronouncing that right, and Trevor Hasty. Those guys are just super geniuses at Stanford University. But I can't believe it. It's a free download. So those are, I mean, obviously you can go to my website, you can go to other YouTube channels, and there's also this free book that is amazing that you can download. So that is my recommendation for if you want to get into the field, where to start.
Yes, so we have another question.
Okay.
Can we have different activation functions within a hidden layer?
I, in theory, you can. Uh, is there an implementation that lets you do that? I don't know. I don't think there is an implementation that lets you do that, but there's no reason why you can't. It would work just as well to mix and match activation functions. The math, doing all those chain rule things is no big deal. Um, so yeah, I don't know. I think that might be a cool thing to try out. So if you're interested in it, give it a shot. I would love to see if there's some like improvements over standard neural networks by mixing and matching activation functions. I just don't know of an implementation that lets you do that off the shelf. So you might have to do some coding yourself. It's not that hard, by the way. I coded the gradient descent algorithm for this neural network that I showed you, and it ended up being like 10 lines of code. It was no big deal.
Yes, so for the next question,
hmm
in a more complex neural network, is there a thumb rule to know how many nodes I should be using in each of the hidden layers?
There's a rule of thumb for, I think there's a rule of thumb for how many hidden layers to even have. I'll be honest, I don't know it off the top of my head. Yeah, you can Google it, but there are, general guidelines on how to configure your neural network from the scratch.
Okay, so how do we choose the learning rate?
Ah, so the good news is we don't. I mean, yeah. So choosing the learning rate is tricky because if it's too excuse me, if it's too big, we'll jump around and we won't converge. If it's too small, it'll take too long to converge, and we can get stuck in local minima. The good news is, I mean, I don't actually know this for neural network implementations, but for gradient descent in general, they have sort of adapting um, learning rates set for you. You don't really have to do it yourself. It starts the way these things do it is they automatically start with a relatively large value. So you're taking relatively big steps at first, and it gradually shrinks it down, just like the step size itself shrinks down. So does the learning rate as you progress over time. Um, and so there's sort of automatic ways of dealing with this. And so 9 times out of 10, you should not have to choose it yourself. Otherwise, um, you can, you can always use cross validation or grid search or something like that to test different values for the learning rate. But chances are you will not have to configure it yourself.
Okay, so what resources do you suggest for using deep learning for image recognition?
Well, in about a month, there'll be a StatQuest on it, so I'll recommend my channel. That's a shameless self promotion. I mean, I had a major, last night I was working on, had a, I had a major breakthrough, and I'm super excited. I've got it all figured out. I cannot wait to make this video. I mean, other than that, I'll tell you what I do. Is I Google it and I just read every single page I can on the subject. I've actually got some of those up open. Let me see if I can tell you some good. Stanford University has some good resources. There's this guy. I don't know if you're familiar with this guy, Jason Brownlee. He's got a website called Machine Learning Mastery. I like his website. I like his blog. I read a lot of his stuff and am inspired by a lot of what he does. Um, anyways, yeah, there's a but yeah, anyways, if I see links to written material that are uh, coming out of Stanford University, I'll usually click on those. And I click, if Jason Brownlee at Machine Learning Mastery, if he has something on the subject, I'll read his as well. So that's what I recommend. So in the meantime, read that stuff. But if you have time to wait, if you don't have an exam tomorrow and you can wait a few weeks, I should have a video on the subject very soon. And I'm very excited about it. It's going to be awesome. All right.
Yes, yes, so are we. Okay, so for the next question, what is the sample size? Is there a rule of thumb x times the number of parameters?
Um, it depends on the method you're using. Um, and yeah, there's rule of thumbs based on the method. And what I would recommend is I don't know if you guys are familiar with the language Python and specifically something called scikit-learn. But scikit-learn, maybe I can find this right now. They've got this really cool flow chart. Let me see. sklearn machine learning cheat sheet. Let's see if I can pull this up. No, it is. If there's this flow chart, it's not cheat sheet. We want to say flow chart. Let's see, here it is. Let me show you this. Boop, boop, boop. Okay, check this out. Um, so they have this flow chart. See it. This is just awesome. So you start at the start, and then it says this is tiny for you guys, so you probably can't see it. Um, you start at the start, and then it says, "Do you have more than 50 samples? If not, get more data." And then it says, "Are you predicting a category?" and you go here, if you're not picking a category, and it asks you how many samples you have. So this thing, it's like it leads you in the direction of what methods you should try, but it also kind of gives you a sense of like how many observations you need to make effective use of. So if you've got less than 100,000 samples, and you have labeled data, then you want to use this linear support vector classifier. If it doesn't work, then consider naive Bayes or k nearest neighbors or blah blah blah. So I'd highly recommend this as a way to kind of learn about what methods you can use when and how much data you need to use it. And again, this is the scikit-learn machine learning map. So if you Google that, you will find it and you will be set.
Yes, so we have a really interesting question now.
Okay.
In a Joshua Starmer world, what should tiny BAM, BAM, double BAM, and triple BAM translate to with respect to underlying emotions for the listener? Is there a different interpretation for each of them?
Of course there is. So, tiny. So, yes, there is a hierarchy of BAMs. So, let's start with BAM. BAM is when, something awesome just happened. It's great. It's, we just stumbled over our first cool sort of moment where we're like, oh, that's what's going on. That's cool. So we get some insight into our data. That's a BAM. Oh, what's a double BAM? Is a double insight. We've gone a little further into the details, and now we're like, whoa, this is crazy. This is awesome. And it's a little better than a single BAM because we're just like, we're learning more. And now we're like, we're in the details, but we're seeing how it all comes together. And then, holy smokes, we keep going, and then we see it all come together. It's like the big picture is finally revealed. We know the details. We see the trees and we see the forest. That's the triple BAM. Oh, we just live for the triple BAM. Um, tiny BAM. Tiny BAM is like, here's a little thing you probably should know. It's not, it's a technical detail. It's not the big picture. It's something that if you have an interview, you're going to need to know. If you're going to implement this in yourself or try to do it yourself, you might want to know this little detail in order to make it work. But it's not something I get super excited about. It's a tiny BAM. So that's where the tiny BAM is on the scale. I think I've had small BAMs too. Small BAMs are a little better than tiny BAMs, but they're still not that exciting. To be honest, though, I mean, obviously I've been honest with you, but to tell you some more about the BAMs, they're actually more than just me being excited about what we're talking about. I'm trying to point out, I'm trying to highlight what the most important concepts are. Where the big ideas? What are the main ideas? What are the things that are worth remembering versus the stuff that we can just look up later, on Google or, Stack Exchange? No big deal. So I try to use the BAMs to highlight those really important moments that this is a fundamental concept. I also use the BAMs to sort of break the video into sort of 3 acts. So act 1, we have a problem and we need to solve that problem. And maybe whatever I'm talking about is a way to solve that problem. Act 2 is the nitty-gritty details, where we're just sort of in the muck. Like imagine this being like some romantic comedy. This is Act 2 is when the two main characters that are supposed to get together, they're actually going in opposite directions. And they're trying to figure out things, and they're like, what do we do? How do we understand the world? Blah blah blah. So Act 2 in StatQuest is we're not actually going in opposite directions, but we're in the muck of things, and we're dealing with a lot of details. In Act 3, the characters come together, and that's also when like we're doing triple BAM because we've got the big picture and we finally see how it all works, and we solve that problem that we set up in the very first act. So that's the hierarchy of BAMs, and sort of not just why I do it because I think it's fun, but I also have some like structural reasons why I use BAMs as well.
Yes, really interesting. Yeah, so for the next question, can you give some ideas of projects for beginners other than predicting house price or Titanic survivors?
Yeah, those are great. Why do people use the same data set every single time? Um, oh, geez. I mean, I'll be honest. On my website, which we were kind of talking about before, I have a few like how to do this in R and how to do this in Python. I try to come up with new and fun data sets. So that's maybe a place to start. I'll be honest, I haven't really thought about it that much. That being said, if you're absolute beginner, uh, yeah, do the Titanic data set once. You don't have to do it more than once. Once you've done it once, you're no longer an absolute beginner. Okay. Excuse me. Okay. Once you've done it once, you're no longer an absolute beginner. And then you can go to this thing called the, what is it called? The UC, is it UC Davis or UC Irvine? UCI Machine Learning Repository. Let me look at this. Hold on. UCI. Yes, it's the UCI Machine Learning Repository. Let me show you this. Here's a great resource um, for getting data sets, and I use it. The UCI Machine Learning Repository, tons of data. It's got the standard iris. It probably has the house things, and it probably has the Titanic data set as well, but it also has tons of other data sets, and you can kind of search for the things that you want to look at. Let's see how we can do that. It's got most popular, newest. Where is the link for? Oh, you can view all data sets here. And on the left-hand side, you can select, do I want to do a classification? Do I want to do regression, clustering, blah, blah, blah. So if you want to like narrow down the focus, you can do that. But what's nice is it kind of, it's got the name, tells you what kind of data type you have, what it's good for, what class it has, um, what kind of attributes they are, how many values you've got, and how old it is. And so this is a great source for just finding like quick, easy data sets that you can play around with. I use it. So I'd recommend if you're interested in new and exciting data sets, you can use it as well.
Yes, yes, right. You can also check Kaggle for some amazing data sets.
Oh yeah, Kaggle, yeah,
Yes.
great source.
So I guess that's it for the questions. However, we
Fantastic.
did have one request earlier.
Uh
Somebody wants you to play a song on neural networks if you have it prepared.
huh. Well, I already did a song at the very beginning. So what you're asking for is an encore. Um, Neural networks are cool. What's the next line to this song? I'm writing it right now. This is totally improvised. Neural networks are cool. You can do them in the morning. You can do them at night. Because neural networks are all right. Bam. All right.
Amazing, amazing. So, for the last question, we have what inspires you to make such a detailed, informative videos, that too for completely free?
uh, what's the inspiration? I'll be honest. The inspiration is you guys. I mean, when I started making my videos, my goal was simply when I was making the video, when I started making the videos, I was working in a genetics lab, and I was working with about 20 other people. They were all doing experiments, and I was helping them with statistics. Um, and it was an academic genetics lab. So I was in a university, and every 6 months we had new students come in and old students leave. And so every 6 months we had people that needed to learn the same statistical stuff. And it was only a few people each month. It wasn't like hundreds of people. It was like 2 or 3 people would show up, and they'd say, "Hey, what's an R squared?" And I'd say, "Well, I'll teach you." Um, Anyways, I kind of got tired of doing the same speech every 6 months, and so what I thought I'd do is make a YouTube video. And the idea originally was that this YouTube channel would only be watched by people I worked with, or friends, or family, or whatever. I had no, I was not expecting anyone else anywhere else in the world to watch my videos. However, they did catch on. Ultimately, I'll be honest. I made my videos for several years before any significant number of people watched them outside of my friends and family and coworkers. It was probably about 2 years before my first video got like 1,000 views. Like one of my videos got 1,000 views, and it wasn't like in a day; it was like cumulative. So over years, it had gotten 1,000 views. And it gradually picked up. And over time, it became clear to me that although I enjoyed helping people I worked with, I was helping a lot more people with my YouTube videos. And um, I was looking at kind of how I wanted to spend my time in my life. Um, I wanted to do the most important thing in the way that I could help the most people. And so I eventually left my job at UNC, at the University of North Carolina at Chapel Hill. I left that, and now I do StatQuest videos full time because the goal is for me to try to make the most positive um, change to the world, or impact to the world. I feel like I'm helping a lot of people. I mean, at least people say this in the comments. They say this was helpful. This helped me pass an exam. It helped me get my degree and graduate. It helped me get a job. And I think that's amazing that I can be a part of these people's lives, even if it's indirectly. They watched my video and it helped them. Um, that's my inspiration. I feel like I feel like I'm doing something that's helpful, and that's what I want to do. I've just always wanted to be a helpful person. Um, and this is the way I found that works, and I can help a lot more people this way. So that's my inspiration. So you are my inspiration.
And you are our inspiration, sir.
Oh, thank you.
So, yeah, I guess that's it for today's session.
Yeah.
It was lovely having you over, sir. Thank you for such a wonderful session.
All right. Thank you.
Thank you.
Okay. Bye, everybody.